So welcome all of you. So today is the fourth session on the structure, stoichiometry, and reactivity of organic compounds and intermediate a problem solving approach. So I am Vijay Rahane, PMRF scholar at IIT Delhi and joint PhD student between IIT Delhi and University of Queensland. So I am teaching assistant for this course. This course is taught by Professor Amit Basak. He's professor from IIT Kharagpur. So we will solve the problem, whatever the content or topic that are covered by professor in the fourth week of this course. So what are the topic covered? We'll just overlook that topic and then we'll solve some problems based on these topics. So in this session, first we have in the first lecture, that is first lecture for this week, and the 19th lecture for the course, that is stereo electronic effect on conformation and reactivity. In this lecture, we have seen some systems like different system of like cyclohexane, different cyclic system, and their effect. If we take the example of this compound, we know the cyclic six membering. It can be flipped to a different conformer like this, right? So in this one, this both methyl group are axial in the B conformation. So, so if you see the population of the conformation, this conformation is major. This is because 3D space arrangement, right? In this, if you see in space, here will be a steric repulsion between these two bulky groups which present at axial position. So the major conformation is the A1 and this one is the minor one. So this effect is a steric effect. So what is stereoelectronic effect? It means this simple effect will consider with the simple example of this. Right. And in this one, right, these two example. So in this one, we know the sulfur having the lone pair of electron, right? So there are two lone pair of electron which are present on the sulfur atom. So this lone pair of electron is localized on the sulfur molecule like this. So if you uh, take another possible confirmation of this by flipping a ring, so which looks like this. right? The lone pair of, of sulfur here present in this fashion. So there will be very low, we can say very low stereo stereo electronic effect here, right? So in this one is the major conformation. So like this many example professor covered in this lecture, uh, which uh, which gives information about the steric effect and stereo electronic effect. With this different such different example, we have understand what is the stereo electronic effects and on conformation and the reactivity of the organic molecule. So in I'll just insert. I'll insert new slide. I'll insert. Right. In this second lecture, we have seen the example of anomeric effect. And stereoelectronic effect. Anomeric effect means we know the if there are such systems present, uh, if it has alpha, any alpha group, right? So in this in such type of systems, if X is equal to oxygen, bromine, chlorine, iodine, such items are there, then uh, the that is in short, if there is polar group present at anomeric carbon means alpha to this or the adjacent carbon of this oxygen, right? Then the axial the X are is lies around at the axial position because of the anomeric effect. And in anomeric effect, why this is major one? Because the non-bonding orbital, if you say the it has the such bonding orbital, right? Its non-bonding orbital is or is stabilized by the lone pair electron pair of this oxygen atom. So that's why the this confirmation is major one. Similarly, in the third lecture, we have covered the Baldwin rule. In the Baldwin rule and some example of the some reaction which in which the Baldwin rule is very important to decide which product is for major and which product is minor one, and also covered a cyclization, enolic systems, and also covered different problems on based on Baldwin's rule. right. So many topics we have covered in this in the week fourth, with mainly majorly the stereo electronic effect and confirmation, uh, stereo electronic effect on confirmation and reactivity of this confirmation. Also the examples, anomeric effect and its example of anomeric effect on and stereo electronic effect. Baldwin rule used in different cyclization reactions. In this one, different cyclization reaction in enolic systems also covered, and problem based on Baldwin rule are covered in the last lecture, fifth lecture of this week. So we'll have some practice problems. We'll take one by one and solve it. So the first problem of this one is uh, the preferred conformation of A is. See, the structure is given, and we need to show which is preferred conformation of this molecule, of this compound. So we'll see what are the main groups are present in this structure. So firstly, the ethyl. We'll split the structure so as we can able to visualize properly. And while splitting drawings, we'll draw all possible. We'll try to orient the group accordingly. Right. So this is the structure, and in this structure we can see there are two lone pair of electron present on the oxygen, right? So they lie like this. In this one also there are two lone pair. So which is preferred conformation in this one? Uh, so if we will look at this four option, the option A, B, C, and D, right? So in this one, we can able to see the first one. In the first confirmation, these lone pair of electron are will be here. In the second one, this lone pair of electron will be here. So we can visualize this by drawing the Newman projection formula, right? So in this one, if you see from this side, if you visualize this molecule from this side, so we can see uh, the front carbon atom, which has one methyl group, one hydrogen, and one methoxy, right? OCH3. And in the back side, we can see here there is a ethyl group, and here is one lone pair, and another lone pair will be here, right? In the second one, for second one, you can, if we draw, the methyl group will be here, hydrogen will be here, and OMe is here, and ethyl is here. Here one lone pair and another lone pair is here. Similarly, we will draw for D, C and D. Here is the hydrogen. Here is methyl. Here is ONE. And backside, the ethyl group will be here. In this one, will where will be the lone pair? Lone pair will be like this, right? So in this one also, if you draw the lone pair will be here, right? And in the fourth structure, you can see, right? The ethyl will be here. Now we can compare the number of gauge interaction for each structure. So if you see the first structure, it has here one butane gauge interaction. Here second, there are two interactions are here, right? And also the stabilizing interaction is also there, right? Since this bond is a polar bond, so its electron density lies more toward this oxygen, right? So the anti-bonding orbital of this will be here, which has vacant electron pair, which is get stabilized by lone pair of electron, right? Present on of oxygen, right? Here, the lone pair of electron on the present on this oxygen stabilizes this uh, sigma star orbital of this bond of this bond, right? So in this one, there are more less Gauge interaction as well as sigma star orbital which stabilizes this one. If you see the other possible structure uh, in these structures, there are no such stabilizing interaction are present. So this stabilizing interaction are present only in the structure A. Right. Here you can easily see. So in these two, there are no such stabilizing interaction can possible because the lone pair are not in the this sigma star orbital. See, those lone pair are not parallel to this, right? Sigma star orbital. So there is no possibility of such stabilizing interaction. In case of this one also, no stabilizing interaction. No, in this one also, no stabilizing interaction. You can say. But if you see this structure, it's having the stabilizing interaction, but the ethyl group make a steric repulsion to this OMe also. So we need to compare these two only. And in these two, so A1 is the preferred conformation for this molecule. The problem second one is the the number of anomeric effects for X and Y. We need to answer the number of anomeric effects possible for this X and Y. So here we will draw the structures. So where are the anomeric effects are possible in this one? First structure you will see in the first structure, the lone pair on nitrogen, where it can be involved in the so this lone pair and can involve in the conjugation for this. So in this structure here is hydrogen, right? So if the lone pair present on the oxygen molecule can stabilize this bond, right? So here one interaction due to the oxygen and another interaction, this bond is stabilized by the lone pair on present on nitrogen atom. So in this structure, one and another, there are total two stabilizing interaction possible for this X molecule. That is, two anomeric effects are possible for X molecule. And for Y molecule, if you see the structure of this Y molecule, in the Y molecule, here we can see the methyl group is at equatorial position. So the lone pair on nitrogen will be on the axial one, and the axial lone pair is not able to involve to give the anomeric effect, right? So due to nitrogen, there will be no any anomeric effect, but due to oxygen, there will be a one anomeric effect is possible for this bond, right? So in this one anomeric effect is there. So this one is a simple problem. Just we need to tell how many anomeric effects are possible for this molecule. So the problem third one is the among the conformation, most preferred conformation for compound B is. So these are the four possible conformation for compound B, and we just need to identify which is most preferred conformation for this B molecule. So we'll draw the uh, uh, anomeric effect possible for molecules, and then we can able to decide. So here we can see in this one, here will be a lone pair present, right? For this one, here will be a lone pair present, right? In this one lone pair will be like this, another will be like this. Similarly, for other molecules, the lone pair. So if you see the structure one, uh, how many possible anomeric effects are there? So there are two anomeric effects are possible, right? Because of this oxygen. One is for this oxygen, this bond serve the anomeric effect, and due to the this is due to the blue oxygen, and due to pink oxygen, uh, here will be a stable. Here will be a anomeric effect are possible. For this structure, there are the two anomeric effects. Therefore, this A structure is the preferred conformation. So if you see other possible structure in this one, to the adjacent molecule, there is oxygen, but this if you see the anomeric effect of this oxygen will be up to here, and so here will be an anomeric effect. But uh, this blue oxygen, if you see, its axial bond is this one, right? So uh, here only one anomeric effect, right? So it is less stable compared to A. And if you see this one, uh, let's say for this blue one, uh, the axial one will be this one, right? Or this one will be a axial bond, but here there is no oxygen. So this one is the equatorial. So here no, here will not be served anomeric effect. And if you see the oxygen, this pink one, for this pink oxygen, for this bond there will be a anomeric effect stabilization. So no anomeric effect. And if you see this structure, it is in the boat form. So obviously this one is the unstable because there will be a lot of steric interaction as the dipolar. Uh, these hydrogens and hydrogen, they are also repel each other. So this one is the obviously the not preferred conformation. But how much anomeric interactions are possible for this molecule? Of this oxygen serve the anomeric interaction for this axial bond, so it has one anomeric interaction. So the compound structure A will be a preferred conformation for this molecule. The next problem is this one is the fifth problem. Among the following, which one undergo SN2 reaction displacement faster? So they have given the four examples, and we just need to tell which molecule undergo SN2 displacement much more faster. So we'll draw the this molecule in the both chair conformation, and then only you can able to decide, because uh, these are the example of anomeric and this molecule doesn't lie in the planar form. So will always try to draw such examples in first in the board form, right? Sorry, chair form first, and then see this one is the, we'll draw the chair, sorry, chair first, and then so this one is the basic skeleton for all molecules. It's same. If you see this one is upward, so this bulky group is be like this. Similarly here also, In all, this bulky group will be up, that is beta, right? So we have drawn it upward. Now the chlorine atom, here you can see the at anomeric carbon there will be the chlorine atom which down upside, chlorine up. Similarly here chlorine down, so chlorine here down. For the third atom, the chlorine is at here but this position. It will look like chlorine, and this one the chlorine at here but the beta, right? So the chlorine will be here. So the uh, the displacement reaction fa- faster, right? For which reaction? So the answer is this. This is because the lone pair of nitrogen able to involve in this, and this can be converted to this form. Right, not delta, it's completely positive charge, and then it get converted by attacking by the attack of nucleophile to the product. This nucleophile then attack here, and then this positive charge will get vanished. So the option 2 is the correct option. So here you can say it since it's equatorial. So for this one there will be a no anomeric effect. In this position, it is not at the chlorine is not at anomeric carbon. So here also there will be no effect of anomeric effect. And here also the chlorine is at equatorial position. So uh, the anomeric effect doesn't help in this conformation also. I will solve the next problem. Major product expected to be formed in the following reaction is discredit the stereochemistry. Means don't consider stereochemistry for this point. Just need to answer the which product is formed as a major product. So in this one, you can see uh, by the addition of the I2, the first will be iodine insertion, right? So iodine will be inserted like this. So both are equivalent, and we don't need no need to consider the stereochemistry as mentioned in the question. So both we can take both are the equivalent, right? So we'll take this side, this one, right? So what are the possibility for to convert to get the product? What are the possibility from here? So the lone pair on oxygen can attack this way or can attack this way. So what is the A possibility? A possibility is the uh, it forms a fourth member ring, right? CH2, I, and the B possibility is the it form a 5-member ring, right? The 5-member ring and iodine will be here. So these two are possibility, that is the option A and option B. So these two products are getting from this one. But if you see this one structure, uh, the 4-exo treat is a favored according to the Baldwin rule. So we have already seen the Baldwin rule, right? In this one, what reaction? This one is the 4-exo tert, and this one is the example of the 5-endo tert. But the 4-endo tert is preferred over 5-endo tert in such systems, right? So this one is the major product, and which option is correct then? So then the option C is the correct option. So this one is the correct one, not this one. These are the uh, incorrect structure. So these are obviously not in the option. So between the choice of this and this, due to the Baldwin rule, the 4-exo tert is preferred over 5-endo tert, right? So the C is the major product. In the next problem is the example of the Baldwin rule only, and in this one, they have given the on reaction, and we just need to tell uh, which is this reaction. So if you see this, see, nitrogen having the positive charge. So this lone pair of oxygen will attack here, right? The maximum will draw it different, so I able to visualize this. So via this center, the nucleophilic attack will be takes place like this, and this what we call the keto enol tautomerization. This we call as a enole, right? And if it open inside, then it's enol exo, and if it open outer side of the ring, then it will be enol exo, right? And inside enol endo. So if you see this one, see, if the ring forming like this and it attack to the some another center, it will be a enol. Here also you can see uh, this keto enol tautomerization, right? So this, because of this, it will be a enol. And how many ring are forming? It forming by enol tautomerization and attack here at this position. So it will be a 6 enol. And since it attack on the ring, and it's a part of ring, that is the bond, double bond open inside the ring. If the bond is open outside the ring, means it's not part of this, it will be a exo. Since it's inside this new forming ring, right? This new forming ring, if you see this new forming ring, so this double bond is inside, so that's why it's endo. So 6 in all endo. 6 in all endo, because 6 member ring, keto enol tautomization, attack taken by keto enol tautomization. That's why it's in all, and the 6 member ring is getting formed, and it's the double bond is inside the ring, opens inside the ring, so it's endo, right? 6 in all endo, and this double bond will be go here, right? And this attack, this form the product is sp3, that's why, and the bond is open inside, so endo trig. sp3, this nitrogen after forming this center, this nitrogen converted into sp3 center, right? So it will be a trig, the ring bond open inside the ring, that's why it's endo trig. So which option is the correct one? The C option, you can say 6 endo in all endo trig. So the option C is the correct option. See, next problem is the formation of pyrazole, that is isomidazole in the following reaction. Which follow path? We need to tell which path is getting followed. So to solve this one, we need to solve the we need to go inside the, we have to look inside the reaction mechanism. So what will be the reaction mechanism for this one? Right, N2H2 means N NH2, right? N minus NH2. So like this will be the structure. NH4. This base abstract one proton from this NH2 NH2, right? NH2 NH2, it OET minus, this OET minus abstract one proton and convert it into right, this minus, this this activated NH form a imine bond with this one. So the product form is the NH2, and here see, this one will be the product one after first step. Then I will just change the orientation so as we can easily visualize the, here will be a lone pair of the electron. So this lone pair of electron can attack here or here, but to form the imidazole, the 5 member ring. So the, here will be, if you give the numbering to this one, it will be first, second, third, fourth, and the fifth. This lone pair attack here. So the 5 member ring is getting formed, right? So this bond NH2 lone pair of nitrogen attack on this carbon. This bond shifts here, and this, the product form I will write here. Right. This abstract a proton from the center, and to form this, to form a product, right? So which type of attack here takes place? We know this one, the 5 member ring is getting formed. So we will write here 5 first, and then the attack takes place the endo attack is takes place, right? The attack after attack, this bond shifted inside the ring. So the endo and the form this center is the sp2, right? That's why it's dig, right? We know all this dig trig, when we should draw this dig trig, all this. So the option, which is the correct option? 5 endo dig pathway. So this A option is the correct option, 5 endo dig. Right, this one is a very simple question. Just we need to inform. We just need to we just we should know the what is the reaction mechanism. Then and then only you can able to understand which pathway is getting followed. Right. So try to practice this mechanism, such mechanism. So the next problem is the most stable conformation of this one. So they have already given the structure, and we just need to tell which is the most stable conformation. So here we can see nitrogen is axial. Obviously, the lone pair will be a equatorial. Here also lone pair will be a equatorial. Here lone pair is axial, lone pair equatorial. So here we need to inform, we need to tell which is the most stable structures of this one. And since it has the lone pair of electron, you can see here more and more anomeric effects are possible for the structure, which that one is the more stable structure, right? Because due to anomeric effect, that bond are getting more and more stable. So you can see here, uh, if we take this first example, so to the first example, it has this anomeric effect is possible for here and here. Two anomeric effects are possible, right? Two effects are possible for this one. This nitrogen, this lone pair stabilize this one anomeric effect possible. For the structure 3, there are methyl is at axial, so 1,3 diaxial interaction is there, right? This 1,3 diaxial interaction present, although it has the two anomeric effect because this, right? Plus, in addition, 1,3 diaxial interaction is also is present here. If you see this, if you compare these two, then you can see it has this 1,3 diaxial interaction is extra, which destabilizes, right? And the anomeric effect stabilizes. So the effect will be less for the C1 compared to A. And in this one, there will be a no anomeric effect because this lone pair not is at the exit position. There it is not able to involve in this. So the structure A will be the most stable conformation because of there will be no such 1,3 diaxial interaction. It has two anomeric effects. So this one is the major structure. We'll solve the next problem. Here detailed solution is given. You can just go through it. I will upload the slides PPT uh, in the common drive. So this one is the another problem. We'll take one or two more problems. So this problem is based on the reactivity. The reduction of the 4 third butyl cyclohexanone with NaBH4 gives equatorial alcohol as a major product. The possible reason could be the transition step trivialized by. So we need to uh, tell this transition state step. What are the factors affecting the transition state and the stabilizing factor mainly? So the options they have given the overlap of the C3 and C6, C3 and C6, C2 and C3 with antibonding orbital of the partially forming C nucleophile bond. See, this one will be not reason. So we will just go understand the mechanism first, and then we can answer this one. See, once this cyclohexanone, right, this one, the hydride uh, NaBH4 gives H minus, that hydride ion, which attacks equatorially, axially or equatorial, right? So if hydride attack axially, then the OH will go to the equatorial position, and then if it attack axially, if it attack equatorially, then the OH will be the axial position. So what are the two possibilities are there? So hydride attacks axially, then this OH will be, this one is the product one, and second product is the, if hydride attack from equatorial position, then the OH will be the at axial one, right? So if you see these possible structures, the Ciplec model, right? Already professor solved many problem on this Ciplex model, right? So in this model, what happened? These hydrogens, as shown here, you can see they helps in stabilizing the antibonding orbital, that is sigma star orbital, right? And because of that, the OH will go to the equatorial position and forms a major product, right? This OH will go to the equatorial position. That's why the nucleophile able to attack at the nuclear attack at axial, and OH will go up, to the equatorial one. So in this one, what are the options they have given? Overlap of antibonding orbital at C2 hydrogen and C6 hydrogen with antibonding orbitals of partially C1 nucleophilic bond, and C option is the overlap of bonding orbital of the axial C2 and C6 hydrogen bond with antibonding orbital of partially forming C1 nucleophile bond. So these are the some options they have given. But if you see the C option, the overlap of bonding orbital of C2 hydrogen and C6 hydrogen with antibonding orbital of partially forming C1 nucleophile, as we have seen in the model. This one is the partially forming antibonding orbital, right? Of nucleophile. So they stabilizes overlap. They overlap with the overlap of bonding orbital of axial C2 hydrogen and C hydrogen. These hydrogens, when nucleophile attack from this position, this partially forming they here will be here there is a overlap and provide some stabilization according to Cplex model. So this one is the reason to form the OH is as a major product. If B hydride minus attack uh, from the equatorial position, then OH will be goes to the axial, and at that time there will be no such stabilizing factor, right? In the transition state. So in the transition state when hydride minus attack axially, this orbital of this C2 and C6 hydrogen, they are have the overlap, a partial overlap with this newly forming orbital. So that makes this OH as a OH at equatorial as a major product. So the option C is the correct option. So the next problem is the possible conformation of methoxy tetrahydropyrene, and 2-methoxy 1,4-oxathione along with their percentage population MNQ are shown, right? And we need to identify a correct statement. So these two are two examples they have given, and we need to tell which one is the major product. So in this one, see the OMe, it has a lone pair of electron in this direction, first case, and the second case, after flipping, since it's ring flipping, right? So this lone pair in the first section, first this one, this lone pair is parallel to the antibonding orbital of this one. Since here there will be a anomeric stabilization, this vacant sigma star orbital of this CO bond is getting stabilized because of this lone pair. So such stabilization is not possible for this one, right? This lone pair, this empty sigma star, not a lone pair. This one is a sigma star orbital. It doesn't have any such stabilization present. So here we can see here clearly the anomeric stabilization present, right? So this anomeric stabilization, so here there will be a overlap, and it makes the compound M, this compound in the M form, sorry, in this form more stable. So obviously the equilibrium of this one will be in this direction more, right? So this one is the major one. and this one is the minor one. Because of this anomeric effect, right? This axial, since this one is the axially present, and this bond gets stabilized due to this anomeric effect of this from the oxygen. I'll make some space for writing the second example. So in this one, see, in this two, if it is A, I have written A here and the B here downward, right? So if you see this one, the lone pair of electron pair present in oxygen, they stabilizes this bond, right? Due to anomeric effect. But we need to consider this lower oxygen, this oxygen having a electron pair, right? And the sulfur also having the a pair of electron. So this pair of electrons, they repel each other because this OM is at axial position and here will be a steric repulsion, right? So this steric repulsion makes this conformation unstable. So it has more pronounced effect, more effect to destabilize this conformation than this stabilizing effect of this stabilizing anomeric effect. So if you see this example here, although it has some anomeric stabilization, but the lone pair present on the sulfur which destabilizes this molecule. So in this one, this molecule lie in the this conformation major, and this one is the minor one. So here there is a repulsion. So in this one, percentage of M is greater than N, and in this one, or it will look like different. So M greater than N, and in this one, Q is greater than P or P less than Q. So this one is a correct option. So accordingly, you can choose where it is correct. So M greater than N, this one is the correct one. But here, this one is wrong. So C here, M greater than N and Q greater than P. So the C option is the correct option. So in this way, we have solved. Here you can say C detailed answer for this one, right? This steric effect, repulsive gauge interaction override the anomeric effect. That's why the this one is the major one. And in the first example, due to this anomeric stabilization, this one is the major. So thank you. Today we have covered almost 10 to 12 problems based on the topics which are covered by Professor Amit Basak. Uh, in the all the problem based on the topics from the fourth week, and in this one the majorly the problem based on the stereo electronic effect. effect, Baldwin's rule, and anomeric effect. Right. So, based on these topics, we have covered some many problems in this session, and I would like to take a question from you guys. What are the problems you are facing uh, while in this topic? You can uh, share, and we'll solve that problem as well. So I will just stop here recording. So you can freely ask a question regarding the topics that are covered. So thank you.